Okay, Thermochem mystery tutorial, question 8. So for question 8, we have DMF. So DMF is given some context of it, similar to gasoline. So you're supposed to write a balanced equation for the complete combustion of DMF. Second part, we're supposed to make use of the bond energy data from data booklet to calculate the enthalpy change of combustion. So first of all, first part, complete combustion of DMF. So DMF, the structural formula is given to you here, CH3, all right, attached to a ring, the molecular formula C6H8O. That will be helpful for us to write the equation. Okay, so first of all, the DMF structure. Notice that state symbols is important. So how do I know that DMF is a liquid? So they mentioned in the question. So state symbols is important in thermochem. So liquid. So the total there are 6 carbon. So as a result, 6 carbon dioxide gas. Balance the carbon first. So 6 carbon, 6 CO2. And then you have 8 hydrogens. So balance it with correspondingly 4 water molecules. Right? And then last but not least, count number of oxygen. So you have 12 oxygen here, 4 oxygen here, total 16 oxygen atoms. Right, 16 oxygen atoms. Okay, so to balance it, you have 1 oxygen here, which means you're left with 15 oxygen atoms that need to be balanced, and therefore 15/2 O2 gas. Alright, so state symbols at standard condition. Oxygen is gaseous, CO2 is gaseous, water is liquid. Okay, so again with thermochemistry, important to write all the equations with state symbols. Then they ask you to make use of a data booklet to calculate enthalpy change of combustion. And then for each of the C double bond O and CO2, use 805. Okay, so for such question, typically my advice to you will be to consider drawing out the displayed formula for the entire reaction. So let's take a look. It's all the bonds shown so that you can count the bonds that are broken in the reactants and the bonds that are formed in the products. Okay, so what I suggest for my students to do to make use of this formula, you basically make use of BERP, bond energy of your reactants minus bond energy of your products. Okay, so a quick way to do this question is to consider all the bonds that are broken. Okay, and this is typically in all in our reactants. So check what are the bonds that are broken. In this case, you have carbon-carbon single bond, carbon-carbon single bond, carbon-carbon single bond, total 3 CC single bond, 2 CO single bond, 2 CC double bonds, and then total 1, 2, 3, 4, 5, 6, 7, 8 CH bonds. Okay, so we're done with this, and then you're left with 7.5 OO double bonds. Okay, so these are the bonds broken in the reactant, all counted for. Then we move on to the bonds that are formed. The bonds that are formed are in your products. Okay, so we have total 2 double CO double bonds in each carbon dioxide. So we have total 12 CO double bonds. And in each water, there are 2 OH bonds. So total 8 OH bonds. Okay, so we make use of this formula. So you can take a look the bond energy of all the reactants. So basically over here, I have all the bond energies of the reactants. 8 CH bonds, 3 CC bonds, 2 CC double bonds, 2 CO double bonds, 2 CO single bonds, and 7.5 OO double bond. Alright, 15/2 is 7.5. And then the products, 12 CO double bonds and 8 OH bonds. Okay, but this is not important. So to me, what's important, quote the formula that you're using so that the examiner know what approach you're using. And then importantly, from a data booklet, find the values that you have. Okay, so from the data booklet, quote all the values here. So you can either refer to the data book, or you can just write down all the bond energy, copy and paste from your data booklet here so to make it ease of referencing. So CH bond 410, CC single bond, there will be 350, CO single bond 360, CC double bond 610, and OO double bond 496. CO double bond, we're supposed to use the values in the given the question, 805, and then for the OH bond given to you is 460 in data booklet. Okay, so important for you is to show in this substitution process. Okay, so again I highlight this is the key working step that you show. Show the substituted values for all the bond energy multiplied by the respective number of bonds we have broken or formed. Okay, and then remember your operators, your square brackets, because you're subtracting all the bond energies that products form. So some of you may be wondering, why do we subtract away the bond energy? Because in this case, the products, these are bonds that are formed. As a result, when bonds are formed, it's exothermic process. So therefore, we put a negative sign to convert all the bond energy to exothermic. All right. So in this case, every time I form a CO double bond, I'm releasing 805 kilojoules of energy. So when I form 12, I'm releasing negative 12, 805 kilojoules of energy. All right. So the rest of it, simple pressing a calculator, you should get a value of negative 3350 kg per mole. Again, from this reaction, you can know that this is a combustion reaction. So have some basic chemistry sense. Combustion, it's going to be likely to be highly exothermic. Okay, so it's highly exothermic, and therefore you expect your value to be negative. Okay, so moving on from this calculation, all right, in part B, the question goes on next to say that you have a sample that's burned, you only trap 80% of the heat. So in this case, it's only 80% efficient. And then what happens is that 200 grams of water, this is your mass of water, 32 Kelvin, this will be your delta T, your 1 gram of DMF. So this is definitely not your M. In this case, this is your number of moles or your mass of your fuel, which means you can find the number of moles of fuel. Okay, so in this case, we are supposed to calculate the experimental enthalpy change of combustion. So let's take a look. We can find the Q equals to mc delta T over here, because we know that water, the C is a very well defined number. The C is just equal to 4.18 J per gram per Kelvin. Alright, so in this case, M is 200, 4.18 is the C, delta T is 32. Alright, so we can work out this value. Once we get this value, 26572, this is the amount of heat that is absorbed. So if you take a look at the question, only 80% efficient. As a result, it means that this constitutes to 80%. Okay, this is your 80%. Because only this amount of heat is absorbed to heat up the water. So 26752 happens to be the 80%. The question now is how much heat is then released from the combustion? So the amount of heat that's released from the combustion of 1 gram of DMF will be the 100%. So from 80%, how do I find 100%? Logically, I will need to do some scaling. So the scaling factor will therefore be multiplied by 100 over 80. And that's what I'm doing over here. 100 over 80 multiplied by the amount of heat absorbed, you get the heat that is released. So this is the heat that is released, the 100%. So only 80% is absorbed. Okay, so again, have some sense of numbers. This is the 100%, of which only 80% is absorbed. So this is the amount of heat produced from 1 gram of DMF. So again, remember this 1 gram of DMF, I can work out to find the number of moles of the fuel burn, because I'm supposed to find the enthalpy change of combustion, which is defined by per mole of your fuel burn, right? The heat per mole of fuel. So can work out the MR of DMF because the molecular formula is given to you. So DMF C6H8O, the MR can be easily found to be 96. So the amount of DMF burned 1 divided by 96, you get your 0.0104 moles. Enthalpy change of combustion is just simply your Q reaction over number of moles of fuel. Remember, defined by per mole of fuel burned, right? So in this case, the negative sign is important because we need to indicate that combustion is an exothermic reaction. Alright, combustion is an exothermic reaction. Okay, so sub in the values of the Q reaction, sub in the values of the number of moles of DMF. Remember, the units is in J over mole, so you end up with J per mole. To convert to the standard kJ per mole, you divide by 1,000. Okay, again, you get a value that is similar, right? Very highly exothermic. Then, in the second part of the question, it said, comment on the difference between this value and that calculated in A using bond energy. So in A, the value given was negative 3350 kJ per mole. So this was using your bond energy method. This is our experimental value. So some of you may be tempted to say that, oh, sure, if this is experimental, therefore there will be heat loss. Okay, this is not valid. Why isn't this valid? Because if there is heat loss, it's already accounted for. I already said there's 20% heat loss. So you cannot account for the difference due to heat loss because in the calculation, we already factored in the heat loss. So why is there a discrepancy then? So take note, okay, when we use the bond energy method, so when we see the example CH bonds, CO bonds, CC bonds, or CC double bonds, where do we get all these numbers from? These numbers are actually what we call average values, which means largely they are compiled from a number of different organic molecules. So any organic molecules as CH bonds, CO bonds, or CC bonds, the values are then computed, averaged out, and then reported in the data booklet. And therefore, these values, average values, and therefore not specific to the DMF in this reaction. Okay, so that's a typical explanation. Why is there a discrepancy between calculation using the bond energy method and the actual value? So typically, we say that, oh, the bond energies are average values. All right. Second, we go back to the definition of bond energy. Bond energy requires, all right, everything to be in the gaseous state. If you take a look at the reaction of DMF and water, right, just now we look at it, it was actually liquid. But when we use the bond energy, we're just treating this entire thing, this entire DMF molecule and the water as though they are gaseous when we just use the bond energy. So think about it. Is it a valid assumption to use the bond energy method then? So the bond energy method assumes that everything is in a gaseous state. Alright, so bond energy values are based on calculations from reaction in the gaseous phase. That means your products and reactants are gaseous. Okay, but in this case, water and DMF, they are liquid at 298 Kelvin and 1 bar. So as a result, there's a discrepancy. So this discrepancy, other than the bond energy values being average, also it's due to the enthalpy change of vaporization of your DMF and water. Alright, your DMF and water are liquid. They need to be vaporized to gas before we can use the bond energy method. So the enthalpy change of vaporization could be a reason to explain for the discrepancy. Okay, with that, we are done with question 8.